What's up? Mr. Mayes is here with you again. This time we're doing goodness, chi-squared goodness of fit. So look, guys, this is just another example of a chi-squared goodness of fit test. I have one up already, but I think actually I can make it a little bit more simplified here version. The other video that I have has a nice long table to it. This is just a different example, a little bit more succinct, but I'm going to go over the same concepts, same type of thing, and what you need to have in your chi-squared goodness of fit test to get a good grade on it. Here we go. Let's take a look at my example. So, a company claims that a batch of mixed nuts contains 51% cashews, 29% almonds, 12% macadamia nuts, and 8% peanuts. To test this claim, quality control inspector takes a random sample of 150 nuts from the latest batch. So he took a random sample. That's important because that will be important for our first condition. So we have counts. Whenever we have multiple categories, so not just two, but more than two, we're going to look at, and they are counts, we're going to look at a chi-squared goodness of fit test. If it was just two categories, we might look at looking at a difference of proportions, but we're actually trying to see if we're taking these proportions, actually not even a difference of proportions, because what we're doing, sorry guys, what we're doing is we're trying to see if these counts or the proportions are similar to what we would have seen otherwise by the company. And whenever we have that situation, we're talking about a chi-squared goodness of fit test. So let's go and run through this guy here. Remember that if we see the word evidence, we know we're doing a hypothesis test. So let's first do our hypotheses. Why are we doing green today? Green, well, yesterday was St. Patrick's Day, so, green. So the null hypothesis is always that whatever we got matches up, or whatever we have, our sample is going to match up with whatever the company claimed. So we're going to say our null hypothesis is that the nuts, the distribution of nuts is the same as what the company claims it to be. I'm going to try to write a little bit nicer from now on here. I had somebody comment that they thought I had chicken scratch handwriting here. Let's just try it because I'm trying to get through it so fast here. So the distribution of nuts is different than the company claims. The alternative is always about things being different, and the null is always about things being the same. All right, so you might want to write that down somewhere. The null is always about things being the same. The alternative is always about things being different. All right, so now our conditions, we have to have these conditions in here. So what are the conditions for inference? I'm going to use a different color just because, it's fun to use different colors. So conditions. What are the conditions for inference? Well, the first one is that we've taken a random sample. So we have a random sample of 150 nuts. Remember that you want to put your context in here. The second is that we have data are in counts and independent groups. All right, we're not going to have cashews in the almond group, right? They're all different groups. And then the other one that's really important here is that our expected values are going to be greater than or equal to 5 as displayed in the table below. Okay, I'm going to go ahead and make my an expected value table here. And I want to make sure that I tell them where I'm like referencing, right? I'm in the table below that I'm drawing is going to have my expected values. So we want to make sure that we do that. And I normally like to draw a table down here because some people like they just put their expecteds right here. But if you just put your expected values right underneath your third condition, then we'll know where it is. So we're going to go, I'm basically going to copy that table down here. So cashews, almonds, macadamia, and peanut, and total. And then I'm going to say observed, which is what I have up there, 83, 29, 20, 18, and a total of 150. And then I'm going to write expected right underneath it. And how am I going to find the expected value? Well, the expected value is what I expect each nut to have if it was equal to what the company says it is. So what I'm going to do is I'm going to take, to find the cashews, I'm going to take 150 and I'm going to multiply it by 0.51. That's going to tell me how many expected cashews that I have. All right, so I'm going to go and do that. And I'm going to get 76.5. It's okay if my expected values are decimals. I really don't want my observed to be decimals. So I want to make sure my observes are all whole numbers and my expected values can be decimal. I'm not really only going to round. I'm just going to round to one decimal place. It really doesn't matter where you go. So we're going to go 76.5 for that. And then for almonds, I'm going to take 150 almonds and I'm going to see how much 29% of that is. All right, so I'm going to take 150 times 0.29. I'm going to get 43.5. And then I'm going to take 150 nuts and times it by 0.12 to get my macadamia nuts right there. So 150 times 0.12, 18. And then the peanuts would be 150 times 0.08. 0.08, right? Here's 8% peanuts, so 150 times 0.08, and that's going to be 12. All right. And that should add up to 150, just to confirm. I'm pretty, oh man, the lights always go out on me. It's because I'm not moving enough here. Okay, it's 150. All right, so it's dark in here. Okay, let me get the lights turned on. Hold on one second. All right, lights are back on. So we're going to say here, we will use a chi-squared goodness of fit test with how many degrees of freedom? Categories -1, so the number of, not cats, I'll just write it out. Because you know, those of you out there might think, how many cats? Do I take my cats -1? So 1, 2, 3, 4 categories -1, which is 3 degrees of freedom. All right, so now we know we're going to do a chi-square goodness of fit test with 3 degrees of freedom. We have our expected values. We're going to do our mechanics. So let's change the color again because, you know, colors are nice. Colors of the rain. Let's go blue here. We'll go blue for our mechanics. So our mechanics section here is what is our math? What does our math look like? So we're going to do a chi-squared test. So we're going to calculate a chi-squared statistic with 3 degrees of freedom. And the chi-squared is going to be the sum of the observed minus my expected values squared divided by my expected values. It's pretty simple. I know that seems like a lot, but you know, it really isn't hard to memorize how to do this. So we're going to go observed, which is 83. This is my observed. My observed is what I got in my sample. Okay, so the observed is always basically my sample count, and my expected is what do I expect it to have been if it was the same as what I was supposed to do. So 83 minus 76.5, I'm going to square that, and I'm going to divide that by the expected. Then I'm going to add it to the next one. 29 minus 43.5 squared over 43.5. And then I'm going to add it to the next one and the next one. Then I'm going to have these guys, see how magic just showed up really fast, and I'm going to add it in my calculator. So I'm going to go stick this in my calculator. I choose to use a TI Inspire, so I'm just going to go and throw this in here real quick. All right, and I choose, you know, you want to put all this in your calculator as much as you can. You want to get all of these in here. And we're going to get 8.608. Let's So we're going to get 8.608. And then we want to find the probability that my chi-squared with 3 degrees of freedom is always going to be greater than or equal to 8.608. So now, if you have the use of a calculator or a computer like GeoGebra, or you have some other Minitab, anything like that, SPSS, and you're going to use, you want to find the p-value. You want to find the p-value because it's the easiest thing to do for our conclusion. So I'm going to find the p-value here, but if you can't use the p-value, you're going to use a chi-square table, which I'll show you in just a second. So let's first do the p-value. So I'm going to go menu, at least in the TI Inspire, I'm going to go menu, statistics, distributions, chi-squared CDF. And by the way, we're always greater than on a chi-squared. 8.608, so we're always going to have a lower bound. Our upper bound, just put a bunch of 9s in there, and we have 3 degrees of freedom. Hit OK, and we've got a p-value of 0.035. 0.035. Okay, there's my mechanics. So now if I can't find the p-value, and by the way, I'm going to split this in half here because there's going to be a conclusion depending on which version you use. So if I can't find the p-value, I'm going to use something called the rejection region. And what that is basically my minimum value of chi-squared with 3 degrees of freedom at an alpha level of, in this case, we're going to use 0.05. What is my minimum chi-squared value that will give me a reject the null conclusion in my hypothesis? So anything bigger than this value is going to reject the null, because it's going to be a bigger chi-squared value. And anything smaller than the chi-squared, we're going to fail to reject the null. That's called the rejection region. So we're really looking for the minimum value for me to reject the null. Anything bigger, again, we're going to reject. So that we use a chi-square table. So let me show you this chi-square table here. So we're going to be looking for, right here are your degrees of freedom. Okay, so we're looking at 3 degrees of freedom. And then over here is our alpha level at 0.05. So we're going to go find our alpha level 0.05, our 3 degrees of freedom. We're going to go over, we're going to go down, and there is our rejection. So that's the minimum value of a chi-squared to make us reject the null. So we're going to write that in now as, what was that again? 7.815. 7.815. So this is the minimum value. If our chi-squared value is bigger than that, then we're going to reject the null. So we know right now that we are going to reject the null because 8.6 is in fact bigger than 7.8. Here we just know that this is going to be smaller, right? This is smaller than 0.05, which is our alpha level. So we know here we're going to reject the null. So both of them are going to lead us to the same conclusion. It's just the way we get there has to be a little bit different. So now we're going to write our conclusion. All right, so this is our conclusion. If we found the p-value, we're going to say, since the p-value of 0.035 is smaller than the alpha level, we reject the null. There is evidence that, and then we rewrite our alternative hypothesis, that the distribution of nuts is different than the company claims. All right. If we use the rejection region, this is what your conclusion looks like. Since the chi-squared value of 8.608 is in the rejection region, we will reject the null. And then we write the same thing as we did there last time there. There is evidence that the distribution is different. The distribution of nuts, sorry, of nuts, I'm going nuts, is different than the company claims. It reminds me of my kids playing this song. It makes me go crazy, have it on loop. Okay, anyway, this is a full-on chi-squared goodness of fit test. There you go, guys. That's all there is to it. I know it took me 15 minutes to go through that, but I gave you step-by-step procedure. We'll catch you next time. Good luck in your stats. You got this, but we're almost done. See you later. Bye.